Okay, we've gone to part E. Couldn't fit this one into 4 videos like the others. So in our final video on momentum in 2 dimensions, we're going to look at spacecraft propulsion, which is our application for this subtopic. And we're going to look at how conservation of momentum can be used to understand and explain the, in fact, 3 different forms of spacecraft propulsion. So let's finish off by looking at our application for momentum in 2 dimensions, which is spacecraft propulsion. And we're firstly just going to consider a rocket. Basically, conservation of momentum is the principle that underlines the way a rocket works. So we have a rocket engine down here that expels very high velocity gas, burnt gas. So it burns the fuel and it expels that fuel at very high speed downwards in this case. So that momentum has a certain fuel. Conservation of momentum says the total change in momentum must be 0. So whatever momentum the fuel has in this direction, the rocket must gain that momentum in that direction. Momentum over time, so change in momentum over change in time is a force. A force causes an acceleration and up the rocket blasts into space. Often once in space, rockets use, well, satellites and other spacecraft use a device called, and I should have written that here, it's over on the other side, an ion thruster. So they might use this to adjust their orbit if they're starting to lose altitude in their orbit or if they need to move into a slightly different orbit. And the way an ion thruster works is it uses ions, and in particular they use xenon ions, which are very heavy, and obviously the mass increases the momentum, and they accelerate them across a potential difference. So we know that positive charge is attracted to negative charge, repelled by a positive charge, so we generate these xenon ions, then they get accelerated. We're going to do a lot more of this on the next topic, so if you're not quite familiar with this, don't worry, but hopefully you know that positives repel, 2 positives repel, a positive and a negative attracts. The ions get shot out the back here because of their mass. They have a relatively large amount of momentum. Then the spacecraft gains momentum as in the opposite direction. So that change in momentum causes a force, which basically causes an acceleration, moving the spacecraft. Another really interesting form of spacecraft propulsion is solar sails. So solar sails make use of the fact that light behaves like a photon. So a photon is like a little packet of light, and these photons have momentum. Sorry, a little mistake there. We can work out the momentum of a photon using this formula. I'm not going to do this in detail now because this is something that we will come back and look at later in the year when we look at light and matter later on, this equation and where it comes from. But just for now, accept that light, even though it doesn't actually have a mass, a photon doesn't have a mass, it can have momentum. So when light strikes something, it is an interaction, and again, momentum must be conserved. So if we think about a photon of light hitting a solar sail that would absorb, now often we represent a photon with a little squiggly line with an arrow. It's not a very good one. But if that photon strikes a solar sail and it's absorbed, we can work out the change in momentum of that photon. So initially this photon will have a momentum. If it is absorbed, basically it comes to a stop effectively when it hits the solar sail. So basically the change in momentum equals the final momentum, which is 0. Maybe I'll write that out. Equals the final momentum minus the initial momentum, which is equal to 0 minus pi. So if we represent the initial momentum of the photon with that sort of arrow, that means that the change in momentum is minus that, so that gives us a change in momentum of a magnitude p. For momentum to be conserved, the sail then must absorb, the sail must gain momentum in the opposite direction of p. Sail gains momentum p in that direction, the equal and opposite. However, if that photon is reflected, something rather unique happens. So if we have a photon initially going in, and then that comes off the sail and it's reflected back this way, PF, we can represent that with a vector, so PI would equal that going towards the sail. I won't write that out again, we've got that there. PF would be down here. If we work out our change in momentum equals PF minus PI, what we get is PF, so I've just transferred that PF from there, minus PI, so it's plus minus PI, do the opposite with a vector, so that's showing that's supposed to be a straight line, minus PI. So we can see now there that the total change in momentum is equal to, in size at least, 2p. So we get when it's reflected, and I guess it's in that direction there. Doesn't, we probably should say, we're saying that's a positive, so we should say a negative 2pi. So basically, sorry, I'll use my laser pointer. We get a change in momentum in this direction towards the left of 2p. Therefore, when it's reflected, the sail gains momentum, but it gains twice the momentum if it was absorbed. So it gains 2p momentum in that direction. So, a sail that reflects will allow more momentum to be transferred to the solar sail, therefore greater force acts, therefore a greater acceleration, and that sail will just keep accelerating as long as light is shining onto that solar sail. There's been talk of also using this technology to get rid of unwanted or satellites that are in our atmosphere that have worn out. So if we attach a solar sail to satellites in our atmosphere, then when we don't need those, or when those satellites are about to run out of fuel or their useful lifetime, if they could deploy these solar sails, we could then shine a high intensity laser beam, which would shine lots and lots of photons at that solar sail, and those photons could be used to push that satellite out of the Earth's orbit, where it's taking up valuable space that A, could be used by other satellites, or risks colliding with things like the International Space Station or other vehicles that are within space and doing lots of damage to very, very expensive satellites. So I think that covers what we need to talk about for momentum in 2 dimensions, and it also covers for what we need to talk about for motion in 2 dimensions. So we're now 25% of the way through the course. Thanks.